ஆமாம் சார்.
அப்பதான் நீங்க அவங்களெல்லாம் எல்லாத்தையும் அட்மிட் பண்ணலாம்.
ஓகே சார், ஓகே சார், ஓகே சார், ஓகே சார்.
உங்களோட இவங்க யாரு சேர்பர்சன் யாரு?
அசீர்.
அவருக்கு அனுப்பிடுங்க. அவர் நம்பர் இருக்கா உங்கள்ட்ட?
ப்ரொனன்சியேஷன் இல்ல, இது வந்து அந்த இது வந்து ஆசிரா, அந்த
ஆசிர் வந்து
பிரசன்டேஷனுக்கு வந்து அந்த சார்
ஜெயபாலன் கென்னடி சார்.
கென்னடி சார். ஆமா.
சரி, நீங்க கிரியேட் பண்ணி அனுப்பி விடுங்க, நான் அவருக்கு ஃபார்வர்ட் பண்ணிடுறேன்.
ஃபார்வர்ட் பண்ணிருங்க. ஓகே சார், ஓகே சார்.
ஓகே ஓகே.
நான் சீஃப் கெஸ்ட் இன்ட்ரோ듀ce பண்ணதுக்கு அப்புறம் நான் கிரியேட் பண்றேன் சார்.
ஓகே 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 ஓகே.
Sangeet sir, good afternoon.
Good afternoon. Good afternoon.
Good afternoon, ma'am.
Good afternoon, Bhagirathi.
சாப்பிட்டீங்களா? சாப்பிட்டாச்சா எல்லாரும்?
எஸ் சார்.
ஓகே ஓகே. என்ஜாய் மேடம், நீங்க இது பண்ணியாச்சுல, லிங்க் போட்டாச்சுல? எஸ்எஸ்டி தவிர மீதி எல்லாம் போட்டாங்களோ?
ஆமா சார், ஆமா போட்டுட்டாங்க சார்.
சார் இந்த கூகுள் இப்ப மீட்டிங்குள்ள இருக்கும்போது லிங்க் கிரியேட் பண்ண முடியாதோ? நம்ம எக்ஸிட் ஆனா தான் பண்ண முடியும்.
இல்ல, நீங்க இதை மினிமைஸ் பண்ணிட்டு பண்ணலாம், கிரியேட் பண்ணி. இல்லனா வெளிய போயிட்டீங்கன்னா உள்ள வந்துக்கலாம். 10 பேர் தான்
இன்ட்ரோ듀ce பண்ணிட்டு நான்
இன்ட்ரோ듀ce பண்ணிட்டு
திருப்பி வரேன் உள்ள.
ஓகே ஓகே ஓகே.
ஏன்னா இந்த கூகுள் மீட் ஆப் குள்ள போனேன்னா திருப்பி நம்ம இந்த இருக்கிற இடத்துக்கு வருது.
ஆமா. எஸ் எஸ் எஸ்.
ஓகே சார்.
இன்ட்ரோ듀ce பண்ணி முடிச்சிட்டு அதுக்கு அப்புறம் நீங்க போவீங்க.
ஓகே ஓகே சார், ஓகே சார்.
சார்.
வணக்கம்.
வணக்கம் சார்.
வணக்கம் வணக்கம். அப்பதே ஜாயின் பண்ணிட்டீங்க. சாப்பிட்டீங்களா?
சாப்பிட்டேன் சார். எக்ஸாக்ட்லி 157 ஏதோ ஜாயின் பண்ணேன். பட் தேர் ஆர் 6-7 மெம்பர்ஸ் ஆர் தேர் அட் லைக்.
இப்போ 20 அரௌண்ட் 20 வந்துருச்சு. 25 வந்துருச்சு.
ஓகே, வந்துருவாங்க மேபி.
இன்னும் ஒரு 1 or 2 minutes மட்டும் வெயிட் பண்ணுவோம், ஸ்டார்ட் பண்ணிடலாம்.
ஓகே சார்.
எங்க மதுரையில இருக்கீங்களா? எங்க இருக்கீங்க?
மதுரை தான் சார்.
ரைட் ரைட்.
உங்களுக்கு லீவா சார்?
ஆமா, இந்த எக்ஸாம் நடக்குது, ஆன்லைன் எக்ஸாம். 8ஆம் தேதி தேர்ட் இயருக்கு முடியுது, ஃபைனல் இருக்கு.
ஓகே ஓகே.
9th இருந்து ஆரம்பிச்சிடலாம்னு பார்த்துருக்கோம். எஃபெக்டிவ் ஒர்க்கிங் டேயா.
ஓகே ஓகே சார்.
சாட்டர்டே சண்டே ஊருக்கு வருவீங்களா?
நெக்ஸ்ட் வருவேன், சண்டே வருவேன். சாட்டர்டே we have a contact class, so Sunday வருவேன் சார். சாட்டர்டே.
சரி சரி. இப்போ நல்ல ஸ்ட்ரென்த் இருக்கா டிடிஎம்சில?
இல்ல குறைஞ்சிருக்கு.
திருநெல்வேலி சென்டர் இருக்கு.
திருநெல்வேலில இப்ப சென்டரே கிடையாது. நம்ம ஏன்னா அந்தந்த ஜுடிஷியல் ஏரியால மட்டும் தான் நடத்தணும். ஸோ
மதுரையில மட்டும் தான் நடக்குது. அப்போ
நாட் ஒன்லி மதுரை, எங்களோட ஜுடிஷியல் ஏரியானா விருதுநகர், தேனி, எங்களோட அந்த டிஸ்ட்ரிக்ட் 4 டிஸ்ட்ரிக்ட் இருக்குல்ல,
ஆமா, என்கேயோட ஜூரிஸ்.
யூஜி ஸ்டூடெண்ட்ஸ்லாம் இருக்காங்களா?
இல்ல ஒன்லி பிஜி அண்ட் ரிசர்ச் ஸ்காலர்ஸ், அப்புறம் ஸ்டாஃப் மெம்பர்ஸ் வேரியஸ் காலேஜஸ்.
ஓகே, உங்க பிஜி உங்க ஸ்டூடெண்ட்ஸ் அப்ப
பிஜி வந்து செகண்ட் இயர் மட்டும்.
ஓகே
சார், அதுலயும் 1 or 2 ஸ்டூடெண்ட்ஸ் தான் சார் இருக்காங்க. மோஸ்ட் வந்து ரிசர்ச் ஸ்காலர்ஸ் தான் சார் இருக்காங்க.
ஓகே மேடம். இல்ல ஜஸ்ட் டு நோ தட் வெதர் அவங்களுக்கு ஏதாவது ஆன்சர் பண்ணுவாங்களா, டிஸ்கஷன் வராங்களா, அல்லது இட் இஸ் வெரி டிஃபிகல்ட். லேப்டாப்போட ஸ்கிரீனை பார்த்து பேசுறது, அதுவும் இந்த கூகுள் மீட்ல நம்ம முகமும் தெரியாது, யார் முகமும் தெரியாது, கனெக்ஷன்ல இருக்கோமா இல்லையான்னு கூட தெரியாது.
ஆமா சார்.
ஜூம் நல்லா இருக்கும். ஜூம் ஓரளவு நல்லா இருக்கு கம்பேர் பண்ணும்போது.
ஜூம்ல என்னன்னா ஒன்லி திங் நம்மளோட ஃபேஸஸும் அந்த சைடுல வந்து நம்ம வச்சுக்கலாம் பிரசன்டேஷன் வரும்போது. இதுல அந்த ஆப்ஷன் இருக்காது. ஸோ பிரசன்டேஷன் எனக்கு வந்து ஒன்லி அந்த ஸ்கிரீன் மட்டும் தான் இருக்கும். ஸோ நீங்க எல்லாம் கனெக்ஷன்ல இருக்கீங்களா இல்லையான்னு கூட தெரியாது, கவனிக்கிறீங்களா தூங்கிட்டீங்களான்னு தெரியாது. அது ஆஃப்டர்நூன் செஷன்.
ஆமா, ஆஃப்டர் லஞ்ச்.
அந்த செமினார்லயே வந்து ரிசோர்ஸ் பர்சன்ஸ் வந்து அந்த பார்ட்டிசிபென்ட்ஸோடைய அந்த ஃபேஸை பார்த்து தான் சார், ஃபேஸ் ரெகக்னிஷன்ல தான் அப்படியே மோட்டிவேட் ஆகி அடுத்தடுத்த இது போயிட்டே இருக்கும் சார். இது இப்ப இந்த ஆன்லைன்னு வந்த பிறகு அந்த இதுவே இல்லாம தான் போகுது. சார் சொன்ன மாதிரி எங்கேயோ அப்படி இது பண்றோம், என்ன நமக்கும் முடிச்ச பிறகு ஒரு ஃபுல் சாட்டிஸ்பாக்சன் கிடைக்க மாட்டேங்குது இல்ல சார். அது இருக்குது.
அதான் மேடம், நீங்க வீடியோவை ஆன் பண்ண சொல்லலாம், ஸ்டூடண்ட்ஸ் வீடியோ ஆன் பண்ண சொல்லலாம்.
கண்டிப்பா சார்.
பார்ட்டிசிபென்ட்மே வில்லிங்கா இருக்கிறவங்க வீடியோ ஆன் பண்ண சொல்லலாம். so that at least ஒரு 4-5 பேர் ஃபேஸையாவது பார்க்கலாம்.
ஆமா ஆமா,
சொல்லிரோம் சார்.
ஸ்வீட்லின் டேனியல்னு ஒரு மேடம் கடைசியா ஓபன் பண்ணிட்டாங்க வீடியோவை. உங்க டிபார்ட்மெண்ட் தான் சார்?
அவங்க இது நாசரேத் மர்காசிஸ் காலேஜ். எல்லாம் வீடியோ ஆன் பண்ணிக்கோங்க.
சொன்னோன்னு ஓடிட்டாங்க.
மேம் குட் ஆஃப்டர்நூன் மேம்.
குட் ஆஃப்டர்நூன். குட் ஆஃப்டர்நூன்.
Good afternoon Asif sir. Personally sir, good afternoon Bhagirathi ma'am.
Good afternoon.
அதனால கொஞ்சம் ஃபார்மலா இல்ல, சாரி.
அதெல்லாம் ஃபார்மலா இருக்குன்னு அவசியம் இல்ல மேடம். ஜஸ்ட் ஒரு குட் மார்னிங் சொல்றதுக்காக நீங்க வீடியோ ஆன் பண்ண அப்புறம் தான் யார் இருக்கீங்கன்னு தெரியுது, குட் மார்னிங் சொல்றீங்க.
சார் உங்களை நான் தான் இன்ட்ரோ듀ce பண்ண போறேன் ஆசிஃப் சார்.
அதனாலயா மேடம்?
செண்பக தேவி, ஆமா, மேத்தமெட்டிக்ஸ் டிபார்ட்மெண்ட், ஆயித்னா காலேஜ்.
ஓகே மேடம்.
ஆமா சார்.
சோ திஸ் இஸ் அட்வான்டேஜ், டிராவல் பண்ணிட்டே கூட அட்டெண்ட் பண்ணலாம்.
ஆமா,
அட்வான்டேஜ் ஆஃப் ஆன்லைன் மீட்டிங்.
ஆமா, சார்ட்ட வந்து நம்ம நோவும் சொல்ல முடியாது.
டிஸ்அட்வான்டேஜ் பத்தி மேடம் பேசினாங்க இல்லையா, ஆர்கனைசர். சோ அட்வான்டேஜ் எங்க இருந்தாலும் டிராவல் பண்ணிட்டு கூட யூ கேன் அட்டெண்ட் எ லெக்சர். அது ஒரு அட்வான்டேஜ்.
ஆமா, இப்போ இந்த கோவிட் பீரியட்ல நிறைய பேர் வொர்க் ஃப்ரம் ஹோமுக்குலாம் அட்வான்டேஜா இருக்குல்ல ஆன்லைன்.
ஆமா, ஐடி செக்டார்ல நிறைய பேர் வொர்க் ஃப்ரம் ஹோம் பண்ணாங்க.
இல்ல இதுக்கு கோவிட் வருங்கிறதுக்காகவே ஆன்லைன் ப்ரோமோட் ஆயிடுச்சா என்னன்னு தெரியல.
இட்ஸ் போத். ஆக்சுவலா கவர்மெண்ட் இஸ் வாண்டட் டு ப்ரோமோட் ஆன்லைன், பட் கோவிட்னால
பிளஸ் ஆடட்
அட்வான்டேஜ். ஆமா,
பட் இப்படி ஒரு காலம் வரும்னு சொல்லி இந்த மாதிரி மொபைல் போன் கண்டுபிடிச்சிருக்கான் பாருங்க.
ஆமா,
மொபைல் போன்
கண்டுபிடிச்சதுனால இதை யூஸ் பண்றோம் சார்.
நம்ம உண்மையிலேயே லாக்டவுன் தான். இதெல்லாம் இல்லன்னா இப்போ கனெக்ஷனே இருக்காது சார்.
எந்த ஆக்டிவிட்டியுமே இல்லாம போயிடும். செந்தூர தேவி லைன்ல வந்தாச்சம்மா?
ஆமா ஆமா சார், லைன்ல தான் சார் இருக்காங்க.
அப்ப நம்ம ஸ்டார்ட் பண்ணலாமா சார்? ஆசிர் சார்?
எஸ் ஷூர் சார்.
பண்ணலாமா?
செந்தூர தேவி?
எஸ்
Sir, start பண்றேன் sir.
Okay.
May I now request Dr. S. Senbaga Devi, Assistant Professor of Mathematics, to introduce the chief guest.
So thank you, Sindhu Devi. Good afternoon, everyone. And this is Dr. Shenbaga Devi from Department of Mathematics, and I take it a great privilege to introduce today's chief guest and guest speaker, Dr. T. Asif, Assistant Professor and Head and in the Department of Mathematics from MK University. And he's a very eminent person, and I'd like to bring to notice that his field of specialization is algebra, graph theory, and his research specialization is algebraic graph theory and commutative algebra. And he has been guiding quite a good number of students, around 2 PhD students and 3 ongoing students are there in his PhD. And he's a MPhil guide, and he has completed around 23 to 24 MPhil candidates so far. And as far as his professional experience is concerned, Dr. Asir has been working as an assistant professor in Madurai Kamaraj College University till date. And he was a DST Inspire Fellow, a UGC Major Project Fellow, and also UGC Kotadri Postdoctoral Researcher in MS University. And he had been a lecturer in St. John's College, Tirunelveli. And he has in a good number of institutes, very renewed in University, USA, Institute for Research in Fundamental Sciences, Iran, in UAE, and also in MS University, India. And he has a lot of ongoing research projects, and his research projects mostly concern graphs. And the titles for some of them are the graphs constructed from additive operator of commutative rings and Mook algebra, and the core of pedagogy of mathematics. And he holds a lot of honors, awards, and recognitions. Like he won a gold medal for first rank in MSc Mathematics, and he's also university second rank holder in MPhil Mathematics. And he holds a lot of leadership programs, and he has presented a very good number of papers in many conferences, seminars, and workshops. And he has a membership in a lot of academic bodies. He is a member of American Mathematical Society. He is a life member of Academy of District Mathematics and Applications. He's a life member of FATRA Academic of India, and a lot more. See, as I read out his profile, it keeps going on. Like, so please join me, audience, in welcoming such an eminent person. And Asif sir, it's a great privilege, and we are really fortunate enough to have you amidst us, such an eminent personality. Sir, the e-platform is now yours, sir.
So thank you so much, ma'am. Thank you so much for your wonderful work. And also I thank all the organizers, the secretaries and principal of this college, for having a nice discussion with this conference. And I welcome you all for the afternoon section. Yes, I know it is very difficult to sit in a classroom in the afternoon, that too in the online platform. So anyhow, I try to do my best in the same way I'm expecting from your side as well. So before going into my lecture, if you have any doubts or any queries at any point, you can please unmute yourself and may raise your questions. So we have about 50 students, so I don't mind about those things. So please, if you have any questions, please let me know. I just share.
Not only 50, 1 minute. I said not only 50. This is going on in YouTube also.
Okay.
So there may be also.
Okay.
Yes.
But anyhow, they cannot able to participate here. So these 50 students are, if actively participate, very actually, yeah, wonderful time for next 50 minutes or 45 minutes. And okay, so let's move on to my. I like to share my screen. My screen is visible, right?
Yes, sir.
Yes, it is visible.
Yeah, thank you, sir. Okay, so today I'm going to talk about something like two graphs that are constructed from commutative rings. From the title itself, you came to know that this title concerns two disciplines of mathematics. One is graph theory, another one is commutative algebra, which means algebra. So I would like to talk about these two things. I hope you have some basic about these two concepts in the previous lecture as well. Anyway, I just like to go from the beginning. And once again, I would like to tell you that if you have any questions at any query at any point, please let me know. Okay. So from the title itself, you may know that this is part of algebraic graph theory. So one of my discipline of research. So there are two types of algebraic graph theory. One is a graph constructed from some algebraic structure. The other one is vice versa. For example, you may know about adjacency matrix and other things. So adjacency matrix is a matrix we are going to construct it from graph. So we are having some algebraic structure from graphs. Okay? So this is one type. So I will give you a graph, then you can be able to move this graph to algebraic structure. That is one type of algebraic graph theory. The another type is the converse of this one, which means we are going to consider some graph from the algebra. So I would like to concentrate on this second topic, which means I'm going to have a graph from some algebraic structure. Especially for this lecture, I'm restricting myself on commutative ring, especially only two graphs. I would like to introduce only two graphs. One is zero divisor graph, another one is total graph. So I hope that I don't want to go deep into the subject, but I would like to give the blames of the things. Okay, so you may be asking me why, when these type of concepts may be introduced and how long these research are going on. So the idea of these type of things is started from Gailey. Actually, Gailey, you may know that Gailey theorem is also there in algebra. So he is the expert on this subject. Actually, he is the founder of such a thing. He have an idea to construct a graph from the group structure. That graph is now used to call it as a Gailey graph. That is on in the 1878. One of the older subject of this type of concept. And I need some of the basic concepts from both algebra and graph theory. Very, very simple concepts. So for that, I need some notations. Throughout my presentation, R is a commutative ring. I like to take the two operations. For our convenience, I will just take it plus and dot. The additive operator and the identity of the additive operator is 0 and the multiplicative operator is 1. And then I just use this notation. X is surrounded by the bracket is nothing but it is generated by an element in R. And another basic concept I need is ideal. I hope everyone should know that the basic definition of the ideal, but just for the sake of completeness, let us introduce this basic concept as well. Let R be a commutative ring. I'm going to take a subset. I may take it as I in a ring R. It's said to be ideal of R. Then it should satisfy two conditions. The first condition should be I plus is a subgroup of R plus. This means with respect to the first operation, it should satisfy two conditions, as we know that closure and inverse. And for the second operation, I need to have one more condition which says that whenever I have an element from the subset and I'm having another element R from anywhere in the ring, then I'm going to apply the second operation. The resulting element should be the part of the subset. If a subset satisfying these two conditions, then I used to call this as an ideal of a ring R. Another one condition with respect to element, I'm going to teach about the unit. Very basic concept. An element X in R is said to be unit if there exists another non-zero element Y in R such a way that X dot Y equal to 1. 1 is nothing but the multiplicative identity, which means those elements which have the multiplicative inverse, we used to call it as a unit. I'm going to collect all those things and then I used to give the notation as U of R. And what about the one more definition? Zero divisor. An element X in R is said to be zero divisor. Again, I need to have one more non-zero element in R such a way that X dot Y equal to 0. So I'm going to consider all these elements. Then I denoted this as Z of R. So Z of R is nothing but Z of R zero divisor, which means it contains all the zero divisor elements. So here I would like to add one more thing, that 0 is the trivial zero divisor. Okay, sometimes in some book they usually denote it as an element, a non-zero element X in R is said to be zero divisor, but it is a typo error that 0 is always a trivial zero divisor. Okay, so and finally one more last definition I require from algebra, very basic, and one more definition. An element, even a non-zero element X in R is said to be regular if X is not a zero divisor in R. Nothing but the element which are not zero divisor, we used to call it as a regular. So you don't please confuse with this regular and von Neumann regular. We used to study von Neumann regular in the post graduation level, but that von Neumann regular is something different from this regular. This regular is nothing but the element which are not zero divisor. Okay. So if I'm having a ring, then I just partiate a ring into two sets. One side is a zero divisor, another side is a regular element, in such a way that I also having some unit element. So just these ideal, zero divisor, unit, and regular. These are the four basic concepts I require from the ring theory level. And the graph theory, basic graph theory, I hope everyone knows about the basic graph theory. So with this basic notation, I like to move on to my first graph. I would like to introduce about the zero divisor graph of a commutative ring. Okay, so this type of graph actually considered by Ivan Beck in the year 1988, which means he wants to associate a graph with the commutative ring with the specific properties of the zero divisor. Okay, so how he consider actually, he defined this graph. So you may know that if it is graph, we need two sets. One is vertex set, another one is edge set. So what is my vertex set? Vertex set is nothing but I am going to consider with all the elements of the ring as vertices, which means my vertex set are the elements of the ring. And what about my edge set? And two distinct vertices, x and y are adjacent, provided that x dot y equal to 0, which is nothing but the zero divisor condition. So whenever I have a zero divisor condition satisfied, then I'm just going to give an edge. Okay, so I'm very clear, right? So this definition is not a tedious one. And whenever I need to have a graph, I need to have a two sets. One is vertex, another one is edge. So the vertex set, I'm just taking the elements of the ring. For the edge set, what I do is just imposing the conditions of the zero divisor. So now I should have a graph, right? So this graph actually constructed from a ring structure. But note that this concept is started in the year 1988. After 11 years, 1999, D.F. Anderson and P.S. Livingston actually modified this definition such a way that the revised definition, and actually they are giving the name of zero divisor graph. So the present scenario of the zero divisor graph is nothing but the zero divisor graph is a simple graph whose vertex set is Z star of R. Z star of R is nothing but the set of all non-zero zero divisors of R. Okay, so set of all non-zero zero divisors has the vertex set, and such a way that two distinct vertices x and y are adjacent, provided that x into y is 0. Okay, so may I know anyone from this group, can you explain what is the difference between these two definitions? First one is about Ivan Beck definition. Second one is about D.F. Anderson. May I know what is the basic difference between these two? Anyone? Please feel free to have a discussion, even from your Tamil தான் பேசணும், you can go ahead. Doesn't matter about the language. யாராவது கண்டுபிடிச்சிங்களா? Anyone find out the difference between? Just unmute yourself and பசங்களே பண்ணியன் சார், hope அவங்க unmute பண்ண முடியும் இல்லையா?
Yes, they can unmute.
Okay. Anybody would like to add what are the difference between these two definitions? Okay, so there is now one. Let's move on. What's the difference between these two with an example? Okay, so I'm having a very basic ring C6. So if you have a note and pen, I would like to take a rough of this diagram of this zero divisor graph. It is better to understand the concept. So if you have some notes and pen with you, please take it and just try to draw the graph. So I'm giving you the zero divisor of the ring Z6. So what are the zero divisors? I already told you that 0 is a trivial zero divisor, and I hope 2 is a zero divisor, right? Anyone can explain why 2 is a zero divisor? At least come forward, especially the PG students of this college. May I know why 2 is a zero divisor? Is everyone is familiar with the integer modulo 6? Integer modulo 6 with respect to the addition operation modulo 6 and the multiplication modulo 6.
2 times 3 is 6. So
yeah, 2 into 3 is 6. Thank you. So 2 into 3 give you 6. Division with 6, the remainder is 0. Therefore, the multiplication modulo with 2 and 3 is 0. Therefore, 2 and 3 is a zero divisor element. Similarly, 3 into 4 is give you 12, which means again is 0. Therefore, 0, 2, 3, 4, these are the zero divisors. Now, you please try to draw this graph. Since it is an afternoon session, I know it is very difficult to give some exercise, but at least to not get much bore of my lecture, it's better to do some exercise. So please, if you have your note and pen with you, please go ahead with your basic drawing of this graph. So I already told you, if you even forget, I just move back to my definition. First, I would like to draw the graph of Ivan Beck. So this is the definition of the Ivan Beck, which means for Z6, what is my vertex set? All the elements of the ring is my vertex set, right? Which means what is my vertex set? 0, 1, 2, 3, and 3, 4, and 5, right? So these are the 6 elements or my vertices. So you just please plot 0, 1, 2, 3, 4, 5. And then you try to given the edges between the vertices. So how to given the edges? If the product of two vertices will give you 0, then you just given the edge. I hope you understand, right? Try to draw this graph. I will give you maybe a minute of time, and then let's see whether you can able to follow me with this definition. So you please try yourself. Someone volunteer from your side, please come forward. What are the adjacencies? Let's begin with 0. 0 is adjacent to what are the other elements?
Yeah, adjacent with
6.
every element. 1, 2,
Yeah.
3, 5.
Exactly, ma'am. So 0 is adjacent to all other elements. So that's right answer 0. But you cannot adjacency 0 with 0. Why? We have to consider two distinct vertices. Okay, in that way, I should not consider 0 into 0 is 0. Therefore, I don't want to give the root. I have to consider a distinct element. So 0 into 1 is 0. 0 into 2 is 0. So 0 into anything is 0. Therefore, 0 is adjacent to all the rest of the elements, which means 1, 2, 3, and 3, 4, and 5. Okay. So what about 1?
One
What are
is
the neighbors of
adjacent
1?
to 6.
Yeah. 1 is adjacent to?
6.
Actually, 6 is not part of C6, right? The elements of C6 is 0, 1, 2, 3, 4, 5. Okay.
Yes, sir. One is
Yeah.
adjacent to 0 only.
Exactly. So 1 is adjacent to 0 only. There is no other adjacency for 1. Okay. So for 2,
3.
yeah, first 0 is already there. Therefore 0 and 3, right?
3.
So the degree of 2 is 2. Okay. So this is what the graph. I hope now you can come understand the thing. So here is the Ivan Beck graph. Okay. So left hand side I draw the Ivan Beck graph. 0 is adjacent to all the rest of the elements. 1 is adjacent to 0 only. Similarly, 2 is adjacent to 3, and 4 is adjacent to both 3 and 0. So this is the exactly graph. Since 5 is not a 0 divisor, 5 is adjacent to only 0 divisor. Okay. So now I will give you the next definition. So next definition is about DF Anderson. Actually, this is we used to call it as a 0 divisor graph. So let's try to draw this graph. Now, so what is the 0 divisor graph? We are giving the notation for this as well, gamma of R. And now the vertex set is nothing but the set of all non-zero 0 divisors of R, right? And my edge condition is same as the previous one, which means what I have to do, what is my vertex set now?
2, 3, 4.
2, 3, 4, exactly. So 2, 3, 4 is my vertex set. I just wanted to leave 0 alone from the 0 divisor. Therefore, 2, 3, 4 is my vertex set. Now try to given the adjacency. 2 is adjacent to 3, and 3 is adjacent to both 2 and 4, right? So that is the graph. So here is the graph of DF Anderson as well. So now you understand why they wanted to change this definition. Why DF Anderson wants to leave some of the elements. You just see that what are the elements they remove from the ring? 0, right? 0.
And other than the non-zero divisor.
Exactly. Other than the 0 divisor. So we have the name for that, right? Regular element. I have given the definition, right? Regular element means which are not 0 divisors. So they just remove 0 and regular element. Why they remove 0 and regular element? You just see that 0 is always adjacent to every other element in the ring, right? So it is obvious. Am I right? So it is quite obvious for every ring, not only for C6. It is obviously true for every commutative ring. Therefore, this property is, and maybe it's not very interesting. If, for example, if I wanted to know the domination number of this graph, then I can easily say that it is 1. So these are the drawbacks are there, that 0 is always adjacent to every other element. Similarly, the element which are not 0 divisor is adjacent to only 0, right? For example, here 1 and 5 are not part of the 0 divisor. 1 and 5 is not here in the 0 divisor. which means 1 into any non-zero element will not give you 0. Therefore, 1 is adjacent to only 0 and 5 is adjacent to only 0. So this is the drawback they identified after the 11 years, and thus they removed this one. Therefore, this is nothing but the subgraph induced by the elements of the non-zero elements of the zero divisor, which is, we used to call it as a zero divisor graph at present. Okay, you may be wondering why this a small modification. I would like to tell you that between 1988 to 1999, only 2 papers are there. One is from Ivan Beck, another one is from B.D. Anderson. They wanted to represent the ring as they wanted to partiate the ring element. For that, they are moving to this graph theory concept and try to give the coloring of. Okay, so their purpose is solved and the theory is also not much developed. But now, after 1999, you just Google it about zero divisor graph, you may find at least more than 300 papers in well-reputed journals. So a small modification in the definition will lead the theory to some unimaginable way of difference. Okay? So, okay, I would like to give you some more examples of very small graphs of zero divisors. For example, if I consider the zero divisor graph of C4, it is nothing but the one dot. So we used to call it as K1 or a singleton point. This is nothing but the zero divisor graph or zero divisor graph of this ring as well. And for example, if you find the zero divisor graph of C9, you will end up with just K2, which is nothing but the connected graph on 2 vertices. And then for C6 or C8, C6 now only we come across, it is nothing but the path on 3 vertices. Again, these 2 rings, for zero divisor graph of these 2 rings is nothing but the K3. So you come to know that there are actually, these are the 4 graphs, 4 connected graphs of vertices up to 3. So you have only one connected graph on vertex 2, and you just have only 2 connected graphs on 2 simple connected graphs. Okay, 2 simple connected graphs on 3 vertices. So these all the graphs can be realized as the zero divisor graph of some ring, right? So you can able to understand that this can be realized as a zero divisor graph of some rings. So now the question is, let's just move on to 4 vertices. Can anyone explain how many connected graphs are there? Connected simple graphs are there with 4 vertices. Does anyone know the answer? If you know the answer, you please let me know. Or otherwise, you take this as a simple exercise. After the lecture, if you're interested, you please go through and try to draw all the non-isomorphic simple connected graph on 4 vertices and try to find how many of them are already exist in the literature. And here I am giving 3 of them. All the 3 can be realized as a zero divisor graph of some commutative ring. So zero divisor graph of C2 cross seed. This is F4 means nothing but seed with 4 elements. So this is nothing but K1, 3. And for the zero divisor graph of C3 cross C3 will give you the cycle on 4 vertices, and the zero divisor graph of C25 will give you nothing but the K4. So I can identify the 3 graphs that can be 3 graphs on 4 vertices that can be realized as a zero divisor graph. So if you try to draw all the connected graphs, not all the connected graphs, all the non-isomorphic simple connected graph on 4 vertices, you will end up with actually 6 graphs. Out of the 6, I have given 3 here. All the 3 can be realized as the zero divisor graph of some ring. Can anyone give you the another graph on 4 vertices? I wanted to have a connected graph. Question புரிஞ்சிருக்கும்னு நினைக்கிறேன். Anyone please? I want a 4 vertex connected simple graph which is not isomorphic to these 3 graphs. It's not very difficult. A simple graph. No one? Okay, what about path on 4 vertices? Is it path on 4 vertices is available here? No, right? Am I right? So path on 4 vertices is not part of here. So my question is, what happened to path on 4 vertices? Is it possible to realize this path on 4 vertices as zero divisor graph of some ring? So this is what the question arises. Actually, the answer is no. I would like to give the proof of this. This proof is very simple proof. That's why I would like to give you the proof flavor of this proof. So what I am going to prove that the connected graph on 4 vertices cannot be realized as the zero divisor graph of any ring. This is what I wanted to prove. Okay, so as usual, I am going to prove this in the contradiction method. So what I am doing is I am considering path on 4 vertices with the labels A, B, C, D. A, B, C, D are the label of the path on 4 vertices, and I am considering corresponding ring. So what happened to my corresponding ring? Suppose this graph can be realized as zero divisor graph of some ring R. Then what happened to that R? That R should have the zero divisor with 5 elements, right? So A, B, C, D are the 4 elements because that 4 are the vertices of the path on 4 vertices. So that 4 elements should be there in the non-zero zero divisor, and again one more zero divisor is 0. Therefore, my zero divisor should contain 5 elements, nothing but 0, A, B, C, D. Okay, am I right? So since by my adjacency, I know that A dot B is 0, B dot C is 0, C dot Z is 0, no other product is 0. For example, A dot C is not 0, right? Because there is no edge between A and C. Therefore, A dot C should not be 0. Therefore, these are the only product give you 0. Okay, so this is what my understanding about the ring structure. Okay, so now I try to find what happened to this A plus C. Okay, it is very clear that if you post product with the B, here I don't even bother about post or pre product because I am here in the commutative ring. So therefore, A plus C into B will give you 0, right? It is always 0. Why? Because that AB is 0 and CB is also 0. Therefore, this product always give you 0. Therefore, since B is a non-zero element, A plus C must be a zero divisor. Therefore, this A plus C is an element of the zero divisor. So what happened to this A plus C? This A plus C is one of the 5 elements from here, right? Since only 5 elements are there in the zero divisor, this A plus C should be one among them, either 0 or either A, B, C or D, one among these 5 elements. Okay, so what happened to some of the choices? For example, whether A plus C is maybe A, right? What happened to in that case? Anyone? If I am considering A plus C is A, then what happened? Suppose A plus C is A, then what happened? I hope you understand, right? A plus C is A, then what happened? It is additive cancellation law is valid in
E
terms
is
of
the
ring.
zero element.
Yeah, C is the zero element. I cancel both the A, then C is 0, but C is non-zero element in the zero divisor, right? Therefore, that possibility is not even exist, right? So A plus C cannot be A. Similarly, A plus C is not C, right? Am I right? Again, if C, again you cancel C, it will give you A is 0, but again A is a non-zero element in the zero divisor. Therefore, A plus C should not be A, and A plus C should not be C. Then to what other choices? Either 0, B or D. So I am going to say that this A plus C should be B alone, no other possibilities. So try to find what are the other possibilities. Suppose A plus C is 0, then what happened? I just post multiply with D, then AD plus CD equal to 0. Again, CD is always 0, right? Because here I am having that CD is 0. Therefore, if I apply this one, I will come up with the AD is 0, but there is no edge between A and D in my graph. Therefore, that is the contradiction. In similar way, if I take A plus C is D, and then I just multiply with B, since CB is 0, AB is 0, and CB is 0, I end up that DB is 0, but there is no edge between D and B. This is what the entire concept. Therefore, all the other 4 possibilities are not possible. Therefore, the only possible thing is A plus C should be D. Similarly, the same step I'm going to repeat it for B plus C. I will end up with B plus D is only possible is C. So therefore, I end up with A plus C is B and B plus C is C. Now I'm going to apply this one. Suppose in terms of B, I'm just applying B is A plus C, right? B is A plus C. Instead of C, I'm going to apply this B plus C. Then I'm having a cancellation law. I cancel these two A and A. Then I will end up with A plus D equal to 0, which means D is minus A. So now I'm considering BD. Instead of D, I can apply minus A, right? So B into minus A, since AB is 0, I will end up this as 0. But what's the contradiction here? Again, there is no edge between B and D. Therefore, I will end up again a contradiction. Therefore, there is no possibilities for A plus C or B plus A. Wherever I move on, I will end up with the contradiction. Therefore, there is no graph exists with 4 vertex or than 4 vertex in terms of zero divisor graph of the ring. Okay, so here very simple proof with just a case by case analysis of the structure. So this is how we are analyzing the elements of the ring using the graph theory. We come to solution. Okay, there are many other graphs of zero divisor graphs that exist. So the flavor maybe star graph or a complete bipartite graph and something like caterpillar and other structures. And there are many other structures also exist. These are the zero divisor graph on 7 vertices and the corresponding rings as well. Okay. So some of you may ask me why you are more interested on these type of ring structures, or why you are wanted to study the interplay between the graph theory and ring theory. So here is one of the beautiful theorem which is proved by Professor Ganesan. Actually, Professor Ganesan is guide of my guide, Professor Tamil Selvam, and he proved this theorem in the math annal. Maybe in the late 70s, it is maybe on 1968, I suppose. So this is a one result which is appear in math annal, which contains about 14 pages of proof. I just read the statement of this one and try to understand the statement and tell me the meaning of this one. Let R be a commutative ring. Then the zero divisor graph is finite if and only if either R is finite or an integral domain. Can anyone translate this statement to the statement of ring theory? Actually, Professor Ganesan proved this theorem in terms of ring theory, not in terms of this type of zero divisor graph, because zero divisor graph exists only in the year 1999, but this proof comes about 1968. Can anyone explain the equivalent definition in terms of ring theory? Okay, let me consider first part. What do you understand the word of zero divisor graph is finite? What it means? Whenever I say some graph is finite means the vertex set is finite, right? What is my vertex set? My vertex set is zero divisor elements, right? So what it means, the elements of the zero divisor, or otherwise the elements of zero divisor is finite. So zero divisor is finite if and only if either R is finite or R is an integral domain. What it means by integral domain? There is no non-zero zero divisor exists. So I can just eliminate that case as well. Integral domain means I only have zero divisors, as zero is the only trivial zero divisor. No other zero divisor exists. Therefore, what the beautiful structure of this theorem is Z of R is my subset, right? R is my entire ring. If my subset Z of R is finite, if and only if R is finite. This is the beauty of this theorem. You always know that the superset R is finite, then obviously all the subsets are finite. It is obvious statement, but I'm just having my subset Z of R only in my hand, and that I know that Z of R is finite. Then I surely don't know anything about the ring structure, but the ring structure is also finite. So by studying a subset property, I come to know something about the superset ring. So this is the beauty of this one. With the subset property, I can visualize the entire ring theory. So therefore, if subset is finite, if and only if the superset is also finite in terms of zero divisor, this is the beauty of this theorem. Actually, it is an open problem for quite a long time, and this is the current scenario of this problem is it is proved for commutative ring and it is proved for non-commutative ring, but still there is no proof exists for discrete lattice theory and other types of ring structure. So it is an open problem for quite a long time, from 1970s to till date, more than 50 years of old problem. So still it is not disproved as well. So the question is, if you're considering any ring other than commutative and non-commutative rings, then the question is, if Z of R is finite, whether if and only if R is finite. This is the question. Okay, so I already told that this is already proved in the literature, but with the proof of 14 pages of proof, which contains more depth on algebra. Now we are going to prove this theorem using the visualization of the zero divisor graph within 4 to 5 lines. So here is the proof structure. So I'm just going to prove it within 4 to 5 lines of proof. So very simple proof for 14, instead of 14 pages of proof in the ring theory, I'm going to give it in 4 to 5 lines of proof using the zero divisor structure. So suppose what I have to prove that, so one side is obvious, right? If R is finite or integral domain, then obviously Z of R is finite. This is obvious side. So what I need to consider is Z of R is finite, which means the zero divisor graph is finite and non-empty. Why I just need to have non-empty? I just avoid integral domain. Then I need to prove that R is finite. This is what I need to prove. Since my Z of R, since I don't have a non-empty subset Z of R, I should have at least one element. So in terms of zero divisor, if you have one element, you should need to have two elements, because if X is a zero divisor, you should, it depends upon another one element, right? Therefore, you should have at least two elements. Therefore, I take these two element, distinct element as X and Y. So which with the property that X and Y equal to 0. And annihilator of X. So I just consider annihilator of X as I. What do you mean by annihilator of X? Those element in the ring, suppose you take it R, what are the element in R such that R into X will give you 0? That we used to call it as annihilator of X. Actually, it is from an ideal. Annihilator of X is always an ideal. That ideal, I just take it as I. From the definition itself, you know that I is always subset of Z of R, right? Because for annihilator of X, you should have R dot X equal to 0. Therefore, this ideal is always subset of Z of R. So since Z of R is finite, obviously I is finite, right? Since I already told that I is an ideal, therefore what happened? R into Y is always an element of I for all the elements of R. This is what the ideal definition says, that if I is an ideal, then by the properties of second property, I come to know that for every element in the R, Ry is an element of the subset. Okay, so if R is infinite, what happens to the so now I am assuming in a contrary way that actually I need to prove that R is finite. Instead of proving R is finite, I am going to consider this as infinite. Suppose R is infinite. What happened? Can anyone explain? You try to draw a true circle, actually like a domain or codomain. First circle, you have the element of ring, and second circle, you just going to apply some Y. The rest of the element is in the right hand side. Okay, so what happened to this? Now my R is infinite, right? I am going to apply this Y. After applying Y, what happened? My resulting element is always a subset of I, right? So right hand side, I am always having I with me. Okay, so since it is an online platform, it is very difficult to draw the graphs. You just draw one circle from that a domain, next circle as a codomain. First circle is nothing but R, the elements of the ring. Second domain is nothing but I. Why? I am just applying Y. Whenever I am applying Y, I will end up an element of the I. Therefore, for every element of R, if I apply Y, then I end up in I. So see that left hand side is R is infinite, right hand side I is subset, which is finite. So this is what the clue. Then what happens? Suppose you assume that for every finite set, if you have only finite number of element here, then this R must be finite. But that is not the case, right? R is infinite. Therefore, what should I have? I should have an infinite set in which if I apply an Y, it will end up with a single element. That is to be always possible. That possibility is that I just take that set as J. So there must be an I in I such a way that the reverse element, so pre-image of this I is, I just take it as J. J is nothing but then set of R element R in R such that Ry equal to I. Okay, so this is an element of I. Therefore, for every element, we should have one subset in the R. This subset should be infinite. So one at least one subset infinite தான் இருக்க முடியும். அந்த infinite நான் என்ன எடுத்துக்கிறேன்? I just take it that as J. Okay, so this is the only assumption. Now the theorem is proved. So if this is the case, then what happened? I should have two elements from here, right? And just taking two elements R and S from J, then Ry equal to I and Sy is also I. Then if I separating these two, then R minus S into Y is 0. Therefore, what happened? This R minus S is always an element of the annihilator of Y. But how many R and S are there? For every element in J, every two element in J, R minus S, you have a different element. Therefore, this J is an infinite set here. For the infinite set, I am having R minus S is the infinite number of elements for which annihilator of Y equal to 0. Therefore, this annihilator of Y is infinite, but that is not the case. Because why? Annihilator of Y is always a subset of Z of R. Even Z of R is finite now. In that case, I should not have annihilator of Y as infinite. This is the contradiction. So by visualizing the elements of the ring using the concepts of zero divisor, even if 14 pages of a difficult proof will come with at least 4 or 5 lines of proof in terms of visualizing the ring element. So visualizing the ring element using the graph theory is the greatest tool to find some of the problems or some of the open problems in graph theory. So this is what this type of graphs and groups, sorry, graphs and rings or graphs and groups, whatever may be the algebraic structure, there is an interplay between these two. Any questions at this point? Okay, so fine. If there is no question, now there are many other zero divisor graph structures also be defined, because zero divisor graph may be defined for the non-commutative rings, near rings, semi-groups, modules, lattice, posets, etc., etc. These are the many other structures for which zero divisor graphs are now studied, and you can find at least 300, 400 papers in the leading journals about these zero divisor graphs. Okay. So from the beginning itself, I told you that I'm going to consider, or I would like to introduce two graphs. One is zero divisor graph. Another one is total graph. For this lecture, I may have another 10 minutes of time. I would like to give the glimpse of this one, the zero divisor total graph of a commutative ring. So in the year 2018, again, the D.F. Anderson, who introduced the concept of zero divisor, another one from Ayman Badawi introduced the concept of total graph of a commutative ring. What's the definition of this total graph? We are going to denote this total graph as T gamma of R is the undirected symbol graph with all the elements of the ring as vertices. So here my vertex set is all the elements of the ring is my vertex set, and two distinct vertices X and Y are adjacent, provided that X plus Y is an element of the zero divisor. So again, I would like to give you an exercise. So please don't mind to take your notes or a rough paper and a pen. Please try to draw this graph. Just an exercise. Otherwise, it is very difficult to fit. So please try to draw a graph of this one, the total graph of the same ring C6. We already know that the zero divisors are 0, 2, 3, and 4. Now try to draw the total graph of this C6. Total graphs of C6. So what is over the vertices? Again, 0, 1, 2, 3, 4, and 5. These are the 5 elements are the vertices of my total graph. So how the adjacency? Adjacency is nothing but X plus Y belongs to zero divisor. Okay, so if you wanted to give an edge, you just wanted to sum both the things, both the elements, and the resulting sum, if the resulting sum is an element of the zero divisor, then you have to give an edge between them. So this is what the concept. Can anyone? So again, what are the neighbors of 0? Yeah.
2, 3, 4.
Yeah, 0 is adjacent to 2, 3, 4. What about 1?
1 is adjacent with 2 and 3.
1 is adjacent to 2 and 3. Is it right? 1 plus 2 is 3, so is an element. 1 plus 3 is 4. So again, there is an edge between 1 and 3. What happened to 1 and 5? What about 1 and 5?
It's adjacent.
Yeah. So 1 is adjacent to 2, 3, and 5. Okay. 1 is adjacent to 2, 3, and 5. Similarly, you just try for 2, 3, 4, 5. A small exercise. So here is the total graph of C6. So I just place the vertices in a different format, that's it. You may be given that 0, 1, 2, 3, 4, 5. But for my convenience of drawing, I just label it in a different way, that 0, 2, 4 is one side and 1, 3, 5 is another side. Okay, so this is a regular graph, right? Yeah. Okay. So since I have another 5 minutes, let me give you the total graph of Z9. The total graph of Z9 is this one. 0, 3, 6 is one side is a K3. Another side 1, 4, 5, and 2, 5, 8. This form a K3, 3. which means this is a disconnected graph. The total graph of a local ring C9 is a disconnected graph. So here is the diagram for total graph of C15. So this is the total graph of C15. Okay, so this only one question I would like to give, whether this graph is regular. I have given 3 examples. With this example, you please tell that whether this graph is regular. First of all, let me ask you this question. Total graph of C6
Yes.
is regular? Yeah. C6 is regular. Regular is nothing but the degree of every vertex is same. Yeah. So every degree of every vertex here is 3. Therefore, this total graph is regular. What about this one? Whether the total graph of C, is it also regular?
Cubic graph.
No, altogether it is a say one graph. Just treat this as a single graph.
No.
Yeah, because the degree of 0 is 2, whereas degree of 1 is 3, right?
Yes.
Therefore, this graph is not a regular graph. So, in general, if I ask you a question that the total, whether this total graph is regular, then your answer is no, right? Then I would like to know what is the degree of this. Can anyone guess what is the degree of this graph? I'm just asking you to guess, that's it. I don't ask you to prove. Do anyone have any guess about the degree of each vertex in the zero divisor graph of a commutative ring? Yes, please. It is just a guess. Just a guess.
Minimum 1, sir.
Minimum 1. Okay. I just wanted to know what's the exact degree. It's not by number. Yeah, please.
R.
R. No, R means R having all the elements of the ring is just a vertices. If even it is adjacent to n by 2, half of them, no. You please see that if I am having an x with me, then x is adjacent to y, means x plus y is an element of the zero divisor, right?
R minus 1.
No. Number of element in the zero divisor, right? Zero divisor எவ்வளவு element இருக்கும் நான் அதை வச்சு தான் adjacency கொடுக்குறேன் இல்லையா? So my degree is mostly depends upon the number of element in the zero divisors. For example, I move on here. What are the zero divisor elements? 4 elements are there in the zero divisor. What's the degree? 3. Okay, so if you come here in terms of C9, the zero divisors are nothing but 0, 3, 6. These are the 3 zero divisors. Therefore, the degree of here is either 2 or 3. So it actually depends upon the number of elements in the zero divisor. Because this is the concept. For every vertex in the zero divisor is adjacent to whom? It is adjacent to z minus v, right? X plus y is an element of the zero divisor. Means if I take that is as z is one of the element in the zero divisor. Then what is my y? Y is nothing but z minus x, which means my x is always adjacent to z minus x for every z in the zero divisor. So this is what the adjacency goes. Therefore, my adjacency looks like the number of elements in the zero divisor. But actually, this is not the answer. Why? Because of we are avoiding the loops, right? It's not actually 4 in terms of C6. If you consider C6, the number of elements in the zero divisor is 4, whereas the degree is 3, right? Therefore, it is not actually the same as the number of elements in the zero divisor, but it is actually 1 less than that. Why? Because of we are avoiding the loop. So now I need to find when we have a loop, when we don't have a loop. When we may have a loop, for example, if I consider V, then V plus V is an element of the zero divisor, then there is actually a loop is there, but I am avoiding that loop. Therefore, in that way, the degree is exactly 1 less. If 2V is not even the element of the zero divisor, then there may be no possibility of the loop over the element. Therefore, I don't have such a eliminating of element. Therefore, in that way, I am having the number of element as a number of elements in the zero divisor as a degree. So degree is nothing but either number of element minus 1 or number of element in the zero divisor. It's depending upon if 2V is an element of Z of R, whether 2V is an element of Z of R or not. It depends. So this graph is a biregular graph. Biregular means if you have only 2 types of degree, then we used to call biregular graph. So this total graph is actually a biregular graph. This is one of the theorems proved by my many, and four other Iranians from four other Iranians. That R be a finite commutative ring. Z of R be a set of all zero divisors of R. Then the following is true. Actually, they proved that if 2 is an element of zero divisor, then degree of V is cardinality of Z of R minus 1 for every vertex, which means this graph is a regular graph. So here a simple algebra comes into play. Whenever X is an element, if you product anything with X, that is always a zero divisor. Suppose X is a zero divisor. If you product X with any R, then that Rx is always an element of the zero divisor, right? Because X dot Y is 0, therefore Rx into Y is also 0. Therefore, whenever 2 is an element of the zero divisor, 2V is an element of the zero divisor for every V. Therefore, in that way, degree of V is cardinality of Z of R minus 1. If 2 is not an element of Z of R, then the degree is actually varying between, if V is an element of zero divisor, then degree is Z of R minus 1. If V is not an element of the zero divisor, then the degree is number of element in the zero divisor. So very basic one, basic type of theorems. So, but both it's involving both graph theory and ring theory. So I would like to stop now because it's almost time. I don't want to take anything beyond the time. So here are some of the references. You just go with the zero divisor graph and total graph. You can find many more papers. So for the zero divisor graph, this is the first paper in the year 1999 by D.F. Anderson and Livingston, which is appeared in the Journal of Algebra. And again for the total graph, which is also be a paper in Journal of Algebra in the year 2008. And still this is a very active research area. Even we have a paper in the year 2021 and other things with my students. So there are many other papers to follow, and most of them are the recent ones. Okay, any other questions? Or if you need any further clarification, please. Any further questions and clarification, please let me know, please.
Okay, if there is no question, then we proceed. Santara Devi?
Sir, may I now request Dr. K. Bakireddy, Assistant Professor of Mathematics, to propose vote of thanks.
So good evening, one and all. It's my honor to propose the vote of thanks of this last technical session. Sir, you are explained the concepts in a beautiful manner, sir. And this is much useful for young research scholars. Definitely they got new ideas and they learned the way how we approach the new concepts. And your talk brought up into another world. We walked along with algebra and graph theory, sir. We have a nice feeling. I think my fellow participants also feel like this. And the interaction with the participants also very much useful in the afternoon session. Thank you, sir. Thank you so much. On behalf of the Department of Mathematics, Adityanar College of Arts and Science, and my dear fellow participants, I would like to thank our speaker, Dr. T. Asir, sir. Really, you gave me a very nice lecture, sir.
Yeah.
And your
Thank
concepts
you so
definitely enlighten our minds and refresh our knowledge. From the bottom of my heart, thank you so much, sir.
Thank you so much. Thank you for all your patient listening, especially those who are raising some questions. I'm really thankful for them. They make the discussion session. So thank you so much. Thank you for everyone in the organization section in the department. Even Payas sir is also be there. So thank you for everyone. If some of the known faces are there, please open your videos so that we came to know. Conference is not about.
I request all of you to switch on your camera.
Yeah, so this is a nice opportunity for the organizers as well. They can take a screenshot of this one
Yes, sir,
for the evidence purpose as well. So for me,
all of you switch on your camera.
Yeah, so for me, conference is not about only knowing the things, new things. It is all about conduct as well. So,
Aruna Sakti, madam, please. Thank you, sir.
அசெம்பிளி பண்ணின் சார் ஸ்கிரீன்ஷாட் எடுத்துட்டீங்களா?
எடுத்தாச்சு.
எடுத்தாச்சு சார். ஓகே சார்.
Thank you sir.
Thank you.
Thank you sir. We'll meet you.
Thank you sir.
We will meet.
So what about the next session on paper presentation? The instruction.
We continue. The link will be sent to you.
Okay sir.
You join that group. We give some instruction and Bhai sir.
Yes sir. Good
afternoon.
Fine. As you sir, how are you?
Fine sir. How about you sir?
Fine.
So let us leave from this group and we will join in the respective group for paper presentation session. So once again, I thank all of you for your nice contribution. Thank you. So we leave from this group and we will join for the paper presentation section.
Thank you, sir. Thank you.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you all.
Sir, thank you, sir.